What's the firing rate of every neuron in the network? Okay. So what that gives us is the output. So the output, we'll call the input X, a bunch of spike trains, the output, call it Y. So that gives us Y equals some function of the input X and the weights in the network. Okay, the connectivity matrix. So these weights correspond to the connectivity matrix, okay? And also it's going to depend on single neuron properties. Okay, so clearly this would be something really nice to have. It would allow us to understand how networks work. We still have a hard problem of choosing an appropriate weight matrix, but at least given a weight matrix, this would be something that'd be really nice to know, and it would give us a relatively deep understanding of networks of neurons. Now, this is a bit hard, and that's hard because of learning. So W, we can think of W as being, W random plus W learned. Okay. And what we've done so far is basically ignored this. So far, ignored learning. Okay, and just focused on the random component of the weights, which may seem like a bad idea, but it turns out that excitatory and inhibitory neurons are relatively, even randomly connected networks of excitatory and inhibitory neurons have relatively complex dynamics. And if you think about it, you have about 100 trillion weights in your brain, and you don't really get that much training data. So the truth of the matter is that you don't really learn that much during your life, so your weights are actually mainly random. So it's sort of a more interesting problem than one might at first think. Okay. So that's the focus, and we need, of course, some equations to start with. So we need some single neuron equations, and what we've chose is linear integrate and fire. So the equations we focused on were the following: tau dvi dt equals minus vi minus e leak. I'm going to put a q here. So q is a type of the neuron. It can be either e or I, depending on whether the neuron's excitatory or inhibitory, and then plus the sum on j of wij qe gje of t minus the sum on j of wij qi gji of t. And remember, gje and gji were inputs from other neurons. Okay, so these are excitatory neurons. And these are inhibitory. Okay. And so this, of course, and so this is a linear integrate and fire neuron. Integrate and fire. And the way it works is, So if this is voltage versus time, this is VI of our neuron Q. So here is E leak, and here is E threshold. So it gets some kind of input, and the input is fluctuating in time. When it reaches threshold, it emits a spike and resets. Okay, and then it goes up like this, emits a spike and resets. Okay, so this is a threshold where it emits a spike. And what we want to do is given the input is, so given this is our input, given that, we would like to actually find the firing rate of our neuron. Okay, so that's a hard problem. So we did sort of a standard trick in sort of mathematical science in general, is we made an approximation, and we actually made two approximations. So approximation one, so all weights were the same. Are the same. And remember, Wij QE basically went to tau V EPSP. They would label Q here, and then, oops, and then Wij QI went to tau GQ V EPSP Q. Okay. So basically, it just said that the inhibitory, and so these things are known as, so this is an excitatory postsynaptic potential. It's the size of the membrane potential if there's a single spike. And what we said is the inhibitory PSPs are scaled by this factor GQ. Okay, so it's kind of extreme. We'll see later on why that's not a bad approximation. So we assume all weights are the same, and even then, even still, we have these temporal fluctuations, right? These PSPs give you some temporal variation, but what we did is to get an estimate of the firing rate, we ignored that. So two, ignored temporal fluctuations. So that means GIE just went to new IE. That's a firing rate of neuron I, and GII went to new II, the firing rate of inhibitory neuron I. So these are either excitatory, I is inhibitory as usual. And that basically what that does is, instead of having these curves, these sort of noisy things, you just go like this, down. And now we can actually calculate this time. Okay. And we did that analytically. And so we can compute the firing rate. Okay. And we have tau spike. Tau spike, I'll write it down, is equal to tau times minus log 1 minus, all right, so it doesn't really matter, NTH, some number, I'll call it 0 over nu E minus G nu I. Okay, for nu 0 it turned out to be about 3 if you remember, correctly. Okay, it doesn't really matter. It's just some function that we could work out. And we're going to actually do something here. We're going to add in a refractory period. So this is refractory period. Okay, so if we just look at this expression, the firing rate nu equals 1 over t spike. So without this tau naught, the firing rate is really, really big. It can go easily to 1,000 hertz at firing rates of only 5 or 10 hertz. So we're going to add a refractory period, and we're going to actually set it to around 10 milliseconds. And that way, the neuron can't fire by more than 100 hertz, which is pretty much what we see in practice. So when we do that, oh, chat, sorry. Okay, so I'm very sorry. What does Q stand for? So Q, good. So you should definitely ask questions. So Q equals E or I. E for excitatory, I for inhibitory. Okay. So yes, definitely interrupt me. I'm kind of because you guys are quiet, I'm kind of guessing how fast to go. And so I can easily go way too fast. Okay, so let me, oops. Yeah. Okay, so when we did that, what we got is that so nu I of type Q equals some gain function phi E of nu E minus GQ nu I. Okay, where phi E was, and then actually, sorry, phi Q. Where phi Q is pretty steep. Okay, so this is firing rate. So this is nu E minus GQ nu I. This is actually 3 hertz. And over here, we'll put 100. And what we found is phi Q, once we put a refractory period in here, what happens is this goes up very steeply to 100 hertz. Okay. And basically by about 6 hertz, it's almost peak. So it goes up, it's a very, very rapidly increasing function of the firing rate. Okay. Now this is the no fluctuations. Okay, so that means we've basically another question. Oh, thanks. Okay. There's no fluctuations where basically we've made this approximation here. So G is just replaced by the firing rates. If you include temporal fluctuations, then of course this thing becomes something like this. Oops. So the firing rate actually looks like this. Okay, so with this, so the point of this is this firing rate's relatively steep. Now we did one more thing just to, this is steady state. So we did one more thing, which was basically, we said, okay, these things actually evolve in time. Approximation, but what it says is if, the firing rates of the neurons are really, excitatory neurons are really high, much higher than nu IQ, the nu IQ is going to increase. Okay. When d nu IQ dt is equal to 0, that's steady state. And at that point, the right-hand side is 0. So that gave us, let's go to the next page. That gave us sort of the set of equations, the Wilson and Cowan equations. Equations. Tau E d nu e dt equals phi e of nu e minus g e nu I, oops, minus nu e, and tau I d nu I dt equals phi I nu e minus gi nu I minus nu I. Okay. So these are nonlinear coupled differential equations, and there was a lot of stuff going on, but really all we did is we started with these equations, made a bunch of approximations, which is basically the weights are all constant, and we place the phi rate by the constant by the right-hand side, and that just allowed us to get sort of expressions for intuition for what these gain functions look like. And they told us the gain functions were very steep. Okay. So neurons, any particular neuron in a network is very sensitive to the average firing rate of the other neurons in the network. And so so the way we solve these things is we basically, we computed, so the steady state is when nu e equals phi e and nu I equals phi I. So you can compute the steady states. So what we did is d nu e dt equals 0, gives us an E null line, and d nu I dt equals 0, gives us an I null line. And what we found was that these null lines had the following shape: nu e, nu I. I think I used blue for excitatory null line. Goes down like this, comes up, like something like that. And then the I null line looks, oops. Don't know what's happening. I null line looks something like this. Okay. So this is I, and dynamics is attracted toward the I null line, and this is E, and this is a stable branch. That's a stable branch, and this branch here is unstable. And this says something fairly sensible. If you fix the excited inhibitory firing rate of all the neurons, so let's say you fix it right there, you can the network can either be dead quiet, all this inhibition is turning everything off, or because of the recurrent connectivity, it fires at a really high rate, and in between there's some threshold. Okay. And if inhibition is too low, there is no steady state where the neuron is dead quiet, because neurons are spontaneously active without input. So that's, in that case, there's only one fixed point. Or if inhibition is really high, it doesn't matter how much recurrent excitation you have, you can't have this high firing rate equilibrium, and you only have a fixed point at 0, basically 0 firing rate. Okay. So this, regardless of how we derived it, this should kind of make a little bit of sense. And what we want to do now is compute the stability of this point right here. Is it stable or is it unstable? And it's a 2D analysis, 2D linear analysis, and this is incredibly important. Okay. And what we're going to do is, this point, we're going to call it, so nu E0 okay. That's equilibrium. At this point, at nu E0 and nu I0, what you have is nu E0 equals phi E of G, of nu E0 minus GE nu I0 and nu I0 equals phi I of nu E0 minus GI nu I0. Okay, so this equilibrium, what we want to do is find out how the dynamics behaves near this equilibrium. Is it stable? Is it unstable? Okay, and to do that, we linearize. We let nu E0, go to nu E0 plus delta nu E. And if you remember from last time, go to nu I0 plus delta nu I. We got the following equations, d nu E0 or d dt. So d dt of nu E0, so delta nu E and delta nu I, equal to some matrix phi E prime minus 1 over tau E and minus phi E prime GI over tau E, sorry, GE, GI over tau I, and over here we had phi I prime over tau I, and we had minus phi I prime GI minus 1 over tau I times delta nu E, delta nu. Okay. And so the question is, so remember what we're going to do. We're going to let delta nu E, delta nu I equal some constants, delta nu E0, delta nu I0 times e to the lambda t. Okay. And this d dt operator just brings out a factor of lambda. So we have d dt of delta nu E, delta nu I equals e to lambda t, delta nu E0, delta nu I0. And that equals our matrix, which will just, actually, let me just copy it. Oops. Okay. Going on here, sorry. My pen stopped writing. Hold on a second. Oh, I know. Okay. So delta nu E0, delta nu I0, and we have in here so if in here a factor of e to the lambda t. Ran out of room, but the point is that the e to the lambda t's cancel. Okay, so we want to solve this matrix equation, and so this is linear algebra that I'm guessing you've seen at some point in your life. The way we solve that is, let's actually go to sort of a simplified version. If you have delta nu e, delta nu I equals a, b, c, d times delta nu e, delta nu I, we can write this as a, there's a lambda here. Go down the previous. Okay, so d dt, sorry, this brings out a factor of lambda. That's important. So we have a lambda there. This is a minus lambda, b, c, d minus lambda, delta nu e, delta nu I. There are zeros everywhere. So this has a non-trivial solution. So this now equals 0. So non-trivial solution when determinant of this matrix, a minus lambda, c, b, d minus lambda equals 0, the determinant is equal to a minus lambda, d minus lambda minus bc equals lambda squared minus a plus d lambda plus ad minus bc. And this is the determinant, d for determinant and t for trace. So this is trace, and that's determinant. Okay, so we have lambda squared minus t lambda plus d equals 0. And that has a solution, quadratic equation, solution lambda equals t plus or minus the square root of t squared divided by 2. Okay, call it lambda plus or minus. These are two eigenvalues, and stability actually, so this is, so the system equation is stable if the real part of lambda plus or minus is less than 0. So clearly we need, for this we need t less than 0. Trace has to be negative, okay? So one way to think of lambda plus or minus on the real axis is, so here's the imaginary lambda plane. So real part of lambda, imaginary part of lambda. So we have, this is minus t, and then if the square root is determinant, sorry. So this is minus t. And then let's say that this quantity here is real. So real. So t squared greater than 4d. In that case, what we have is so this is, oops. So these 2 points here are minus are t over 2 plus or minus the square root of t squared minus 4d over 2. So clearly we need, if we want both of these to be negative, we want the square root of t squared minus 4d has to be less than t, okay? This quantity here, this distance from here to here can't be too big. If it's too big, then this blue thing pops over there, and we end up with positive real parts. If we square both sides, we get t squared minus 4d less than t squared, which implies d is greater than 0. So we need d to be greater than 0. And that's true even if this quantity, so d can be really big, right? This can just become imaginary. If that becomes imaginary, it's no problem. It doesn't affect anything. So condition for stability is 1. Oops. So first of all, we need 1. So stability, okay, something is off. So stability, we need 1 t less than 0 and 2 d greater than 0. Okay, that's a general statement about two by two matrices of this form. So let's go back to our matrix. Let me copy it over. Let's see if I can get the whole thing. Okay. Go back to our matrix. Let's get rid of this. Get rid of this. So this is our matrix, right? And the trace T is equal to, oh, these should have been primes. Phi e prime, the slope of the gain function, minus 1 over tau e, minus phi I prime gi plus 1 over tau I. Okay, and the determinant is 1 over tau e tau I times, it's, remember, it's this times that minus that times that. We're going to switch the order. Then we're going to write phi e prime, and this should be a g, gi times phi I prime minus phi e prime minus 1 phi I prime gi plus 1. Okay, so stability, we need t less than 0 and d greater than 0. So it turns out, I think this is in the notes, For this configuration, with inhibitory nuclein crosses excitatory one from below, this guarantees determinant is positive. Okay, so the only thing that matters for the stability, so this one, check, that always holds. So the only thing that matters for stability is whether the trace is less than 0. Okay, and that happens, that always happens if tau I is small enough. So fast inhibition guarantees stability. Okay. In some sense, we're going to see in a second, that actually makes a fair amount of sense. Let's go back to our picture of our nucleins. New E. New I. So the excitatory one comes down like this. And the inhibitory one comes up like this. Okay. Now, if you look at trajectories, let's go green. So let's put in the direction of the dynamics. So if you start here, you push to the right and pulled up, and you can basically, you can spiral in. So this is the case T less than 0, it's stable, or you can spiral out. So come up here, cross like that, and go out and end up with a limit cycle. Okay, so this is T greater than 0. Okay. So what does this tell us? So it tells us a couple things. So one, the conclusions. So one, so EI networks can have a stable low firing rate equilibrium. Two, they tend to oscillate. Okay, so these oscillations, this magenta line, right? If you're in this regime where you're unstable, you go around like this. That's an oscillation. Okay, and oscillations are actually ubiquitous in the brain. If you stick a electrode in the brain, you see them all the time. And then because of this excitatory inhibitory connectivity, this is the case where this is T greater than 0. But even if T is less than 0, because of fluctuations, they tend to oscillate even if T is less than 0. And that's because, actually I'll use this, that's because, remember, this is a firing rate model, but in fact, neurons receive fluctuating input. So even if this is stable, you'll tend to, like, these fluctuations are going to tend to have you oscillate around this curve. Okay. And so you see these oscillations in the brain all the time, which we take as evidence this is a reasonable model. Okay, so let's take 30. Yeah, let's take a 5-minute break. So when I come back, so actually I'll tell you what we're up to. So remember here, we made this really strong assumption that all the weights were the same and the fluctuations are small. And we're going to see why both of those are pretty reasonable approximations. And we're going to do a little bit of averaging. That's sort of the most important thing you can possibly take home from this class, or any class. And so we'll understand what happens when we drop these assumptions and whether or not it's a big deal or a small deal. And then if we have time, we'll start on with structured connectivity. Okay, so let's take a 5-minute break. Feel free to ask questions during the break. You're right here.
Yes. Hello, Professor. Can you hear me? Hello, Professor.
Yeah, there's a bit of an echo. Let me
就是有回声，你要不到这里来说，你把你的那个
You can also ask in the chat, but
不是这个要放出声音出来。我想说把这个声音关掉，给你自己倒是可以。
Okay. I have a question.
sure.
Why the fluctuation will make it tend to oscillate even if the t is smaller than 0?
Okay, so you mean why do we have oscillations even when it should be stable?
Yes.
Is that the question? So it has to do with the fact that
但是这个我不能放，我放的话就会回声。
so if you look at the green curve, let's make a new make a new picture. Oops. Okay. So here's our fixed point. And let's say that we're going to do the green curve. Let's say the trace is negative. Okay, so if we start here, we're pulled up, we go around, we fluctuate in, okay? But we actually go around a couple of times. We don't go straight to the fixed point. And so what that means is that the dynamics looks like, if you plot the firing rate, if you were to plot the firing rate versus time, this is, we'll do blue for new E, it actually oscillates. It's a damped oscillation. Okay, so that's blue E, and the inhibitory firing rate sort of follows it. In some sense, it's really obvious, right? Excitatory firing rate goes up, the inhibitory firing rate goes up. That drives excitatory firing rate down and up and then down, but it's damped. Okay, so red is, this is new I, and blue is new E. Okay, so you get damped oscillations, but what happens in a network with spikes is the spikes cause fluctuation. So every time it gets a little kick, I'll just do the I'll do excitatory only. Let's say it got a little kick, the firing rate gets pushed up, then it oscillates again. Okay, gets pushed up, it oscillates again. So every time it gets a kick, there's these oscillations. And because of noise in the brain due to spikes, it's constantly getting little kicks. So what you really see, so this is, so the green is noise free. There's the green. So this is noise free. If you plotted this in the same regime with trace less than 0, let's be clear. So t less than 0. Once you add noise, what happens is you tend to be sort of just wander around here and kind of, I've had made plots like this. It kind of looks like that, but there's sort of on average oscillation with noise. And again, 2 lessons here. Okay. Did that mainly answer your question? A bit long-winded, but I think hopefully you get the idea.
Thank you, Professor. I got it. And I wonder, I have one more question.
Sure.
In the map, how can we get the blue arrow and the red arrow? I mean, the direction of the arrow, how can?
Oh, okay, got it. Good. That's a very important question. So let's go back to, so the first observation is that on the hair line, so on this line, the new EDT equals 0. And on this line, the new IDT equals 0. That's how we constructed those lines. And so that means when you cross the line, when you go from, let's say, this side to this side, the arrow has to change sign. And that's kind of nice because basically what it means is we need to find the direction of the arrow only at one point in this space and we're done. Okay, so this is new E, this is new, oops. Okay, so this is new E axis, this is a new I axis. So let's go back to the equations. The equations are, they're right here. Okay. So if you look at these equations here, if new I gets really, really big, then the new EDT is negative. So at large new E, the error has to be to the left. Okay, so that means we can immediately put this arrow here, like that. Okay, and when we cross the arrow, it has to be in the other direction. And of course, this region here is actually connected. So the arrow has to be to the left over here. Oops. So it has to be to the left over here. And we can do the same thing for the inhibition. So if you look over here, it's the same deal. When new I gets really large, oops. When new I gets really large, tau d new I dt is negative. So if we go over here, that tells us that arrow up here is downwards, and it's got to be upwards here. Okay, that kind of makes sense. So really, we're heavily using the fact that we're heavily using these two facts. It's 0 on boundaries, and so all you have to do is find the arrows in one point, and we're done. Make sense? Okay, so let's go. Okay. So what I'm going to do now is go back to another question. Okay. Okay, so what I'm gonna do now is go back to our equations. And so ask what happens. So we're going to do this in stages, okay? So in stage 1, we're still going to let GJ, oops. We're still going to let these to go to new JE. We're still going to ignore temporal fluctuations. So we can still ignore temporal fluctuations. Okay, but we're going to take into account, we're not going to assume, but we won't assume that Wij equals a constant. Okay. And what I'm going to tell you now is basically one of the most important things you can possibly know if you're going to have a career in neuroscience, or in fact, almost anything. Okay. And that's basically the following. So, oops. So let's just call, okay. So let's call HI. I'm going to drop this thing. We're going to sum on J of Wij nu J. So I think it's going to drop the Q's and E's. So this is the kind of thing we want to understand, right? So over here we have Q's and E's, but we've let Gj equal to nu J, and this is the same thing, but we've dropped the we just dropped the superscript, so we have less clutter. And what we know is because each neuron has about oops. So each neuron gets about k inputs. We're going to sum this from 1 to k. Where in the brain, k is approximately equal to 1,000. So a neuron gets 1,000 inputs. And we want to know what, and so in the past, we let Wij equal to constant. So what we're going to do now is let Wij equal to W bar plus delta Wij. And these are random and independent. So they're just basically noise. So HI now equals a sum on J, 1 to K, of W bar nu J, plus the sum on J of delta Wij nu J. Okay, and this one here we already know. This is just K times W bar times the average value of the firing rates. Okay, so nu is 1 over K, the sum on J of nu J. Okay, so that's the term we used before. What about this term? Okay, how big is it? How does it scale? How does it depend on delta Wij? And that's what we're going to focus on now. And that's what I want you to pay very close attention to. It shows up. So some of the stuff I've been using is kind of specialized. The techniques, analysis of that term shows up all the time. Okay, we're going to find, so we'll define delta HI, oops. Delta HI equals the sum J equals 1 to K of delta Wij nu J. Okay. And so this is this is so this is different for every I. For every I. Okay. So what is it on average? So average of delta HI equals 1 over K, the sum on I of delta HI is equal to the sum J equals 1 to K of nu J times 1 over K, the sum on I of delta W I J. Okay, so this term is 0 on average. Okay, so this is basically 0. Depending how if you do statistical average, it's exactly 0, maybe it's approximately 0. But because the delta Wij is 0 mean, delta H is 0 on average. So what about its variance? Okay, so this is the important term. So 1 over N, 1 over K, the sum on I of delta HI. You want to square this. Okay, so this is 1 over K, and we have two terms, the sum on J of delta W I J, nu J. Oops, we have here the sum on I. Hold on a second. So the variance, we got that completely wrong, is 1 over K, 1 over K, the sum on I of delta HI squared. Okay. So this is delta HI, and we have the sum on J prime of delta W I J prime, nu J prime. Okay, so basically we've just, this is delta HI, and this is also delta HI. So we basically, but we step two separate sums, and the reason we do that is this is 1 over K, the sum on I, and the sum on J and J prime of delta W I J, nu J, delta W I J prime, nu J prime. I'm going to rearrange terms, 1 over K, the sum on J of nu and J prime, nu J prime, times 1 over K, the sum on I of delta W I J, delta W I J prime. And we want to get rid of this one. Okay. So this is just algebra. We haven't done anything else. And now here's the key observation. These are independent. Delta, if J is not equal to, oops, I need a writing. This is J prime. Okay. So this term and that term are independent if J is not equal to J prime. These are independent random variables. So this is basically what we mean by random. The weights are completely uncorrelated with each other. And so that means this quantity here, so this quantity here is, so 0, oops. So this is 0 if J is not equal to J prime. Okay. So what that means is this is maybe approximately equal to the sum on J of nu J squared times 1 over K, the sum on I of delta W I J squared. Okay, this is just algebra, but basically it's when, because these things are independent, things massively simplify. And now this quantity here is just the variance of W. Okay. And it's pretty much independent of J. Okay, the variance, so this is, and so when all is said and done, so 1 over K, the sum on I of delta HI squared is approximately equal to the variance of W times sum on J equals 1 to K of nu J squared. And this thing is equal to K times the variance of W times the average value of nu squared. Okay, basically what I've done is I put a 1 over K here and a K here, and this quantity here is by definition the average value of the square of the firing rate. Okay, and if you know about the central limit theorem, it's the same derivation. Uncorrelated, you add a bunch of uncorrelated random variables, a K of them, and the size scales as K. Okay, so what we have is that HI so the variance of HI is equal to K times the variance of the weights times the average value of firing rate. Which means we can write HI itself, and turns out that, is the square root of all this stuff. K variance of W nu squared bar times squiggle I, where squiggle I is a zero mean unit variance independent random variable. Random variable. Okay, it happens to be Gaussian, but we won't need that. So if we go back to what HI is, so remember HI, let's go up to here. HI, the first term of HI was just this, right? And the second term is what we just wrote down. So we have HI equals K average value of W times the average value of the firing rate plus the square root of, the square root of K times the square root of, actually, I'm just going to call this, give this a name, sigma W times the square, basically the square root of the average value of the firing. Square root of the square. So basically the same order times squiggle I. And again, the squiggle I is the same zero mean unit variance, right? Zero mean unit variant random variable. And we can write this as equal to K W bar nu bar times 1 plus 1 over root K sigma W Actually, I'm not gonna. Sigma W over W bar, the square root of nu squared bar over nu bar, squiggle line. And what's important is this factor of 1 over k. So when k is small, when k is large, this term is small. Okay, so this is a really, really insanely important take-home message. And it's so important, I'm going to review a little bit what we did, okay? So the key observation, or the key step, was this. We said W includes mean plus random and independent fluctuations around that mean. And that gave us the mean, gave us this term, which scales with k, the number of terms in the sum. And the variance, the variability gave us this term. And so these terms are basically positive just as often as they're negative. Delta Wij is fluctuations around the mean. Sometimes it's positive, sometimes it's negative. So on average, this term is 0. Okay? But it's not, even though it's 0 on average, it does have a variance. It's not exactly 0. And its size scales as, using this calculation, which is sort of just algebra. So all this here was just algebra, but it's one of the most important pieces of algebra that you can possibly do in your life. So you should definitely double check, definitely make sure you understand it. And there were approximations going on here, okay? And if you look in the notes, I make those a lot more rigorous, but they're pretty reasonable. And what you end up getting is the variance scales with not k squared, it scales with k. Okay, so the variance scales with k. That means the typical size of h scales as a square root of k. Okay, and that's basically one of the most important facts you can use. We use it all the time in science. It's basically why averaging works. And what it means is that the fluctuations around the mean are kind of small. They're kind of small, but they turn out to be also pretty important. So remember that our gain function, well, actually, let's write down our steady state. Our steady state equation for nu I q, remember, is equal to phi q times nu e minus g nu I. Okay. And now we can add in these random terms. There's an excitatory one plus squiggle IE. Actually, I'm going to write down plus fluctuations. Okay, and that's basically different for every neuron. Remember what these were. This is basically W bar times K, or WQE bar times K times nu E minus G nu I, more or less. And then we have root K times the variance of WE, the 1/2, times average value of nu E squared, times some random variable, plus root K variance of the inhibitory weights. I'm being sort of times nu I squared, and squiggle I. And so what that means is that, and so what happens is, if you go back and look at the analysis, the WE bar in this case can be really big. So it's okay if we're only considering the first term. So WE bar can be big. And basically what happens is that forces nu E be approximately equal to G nu I. Actually, GD. Okay. But this term over here, these terms, this is actually a very important part. These terms, they can't be too big. Okay. And the reason they can't be too big is because they're going to go inside the gain function. What we're going to get is nu EQ IQ equals phi Q. And I'm going to put, actually what we have here is K tau. Actually, I do K KW Q bar nu E minus G Q nu I. Okay. And then plus in color, and then plus two terms, right? We have a root K times variance, the square root of the variance of the firing rates, variance of the weights of the excitatory weights times nu E squared bar times the square root, squiggle IE, and then plus root K, the square root of the variance, excitatory, inhibitory weights, nu I squared, the 1/2, squiggle II, okay? So these quantities here can't be too big. So that's basically, we call them order 1. So even though root K is pretty big, right? If the variance of the weights, if the weights were 1, this is 30, and we know 30 has a huge effect on the firing rates. So what we have to have instead is that the weights, basically the weights have to scale Wij scales 1 over root K, okay? And what that does is now give you a nice spread in firing rates, right? So these terms here, now vary by, as squiggle varies, they just vary by, 1 or 2. And that gives a nice range of firing rates. And what we see in the brain, of course, is firing rates do have a range. And this is all consistent, okay? So in some sense, the key take home of this analysis is these fluctuations are smaller by this factor of root K relative to the sort of the main driving terms. But they can still, because of this cancellation here, so these cancel, so this term becomes important. And it can't be too big or too small. If it's too small, if the weights are really small, all the neurons have exactly the same firing rate, which is not observed in the brain. On the other hand, if they're really big, the firing rates have too big a range. Some are at 100 hertz, some are 0 hertz, and that's not good either. So the weights, the size of the weights has to be finally, set to some value. It's kind of interesting. The brain can't really choose the size of its weights. It can't make them too small or too big. Well, it could make them too small, but experimentally, it certainly can't make them too big, or you'd have neurons firing at a really high rate and really low rate. Things wouldn't work very well. And for some reason, the brain has decided to make them big enough to give a spread in firing rate. Okay, so I think, so we can also do, there's one more thing I can do very briefly, and that's look at temporal fluctuations. So temporal fluctuations are the same, it's exactly the same idea. If we go back to our equations, okay, let's now consider the case where we do include fluctuations and see what happens. And again, it's the same deal. They should scale as root k because there's zero mean fluctuations. And that's a pretty easy calculation. Again, I'm just going to write a slight abusive notation. We're just going to write hi of t now. Oops. All right, hi of t equals the sum on j of wij delta gj of t. So this is zero on average, okay? So hi of t, a time average of hi of t, average over time equals zero. And that's because these things are zero on average. But what about the square? Again, we can compute 1 over k, the sum on I of hi squared. And it's going to be the same thing as before. 1 over k, the sum on I of the sum on j and j prime of wij prime, delta gj of t, delta gj prime of t. And we're going to average this over time. So we'll average this over time. Average this over time. So we'll assume these are uncorrelated. That actually turns out to be true for very complicated reasons. In time. So when that happens, which means that delta gj of t, delta gj of t prime equals 0 if j is not equal to j prime, and average value of delta gj squared of t when j equals j prime. So when we're all done, said and done, we get the usual thing. We get sum 1 over k, the sum on j of wij squared, and then average value of gj squared. Average over time, or delta gj. And this thing is proportional to okay, so we have sum on j. So this is 1 over k. Sort of, we have two factors of k. We have k from the sum on I. We have a factor of k from the sum on j. And this is more or less, very loosely, w squared delta gj squared. And that's proportional to k. Okay. So that means hi of t is also proportional to root k. Again, root k times the size of the weights. And it's root k times the square root of w squared times the square root of delta g squared. So remember this quantity here, this thing is independent of k. So it's exactly what we saw in the previous statements, previous slides. It's root k times variance of the weight is just an order 1 quantity. It's not too big, not too small. The same thing happens here. So just like the fluctuations from neuron to neuron, the fluctuation time are not that big. They're order 1, but they're enough to drive the neuron to enough to basically give some variability in the firing rates. Okay. Okay, so I'm going to recap a little bit, and then I'm going to give you a preview of what we're going to do next time. So it all started with, let's see, where are the equations I want? It basically, our starting point has always been this set of equations. Okay, and we've made various approximations. The first thing we did is we said, okay, the weights are all the same, and we're going to ignore temporal fluctuations, and that allowed us to derive a firing rate. It seems like a bad assumption, but what we've shown reasonably, it's not really that bad if k is large. If each neuron receives input from a lot of others, the fluctuations are reduced by a factor of square root of k compared to the mean. But they were still important because the fluctuations were still important because of where is it? Because of this cancellation. Okay, the excitatory and inhibitory nearly cancel each other, and that left these terms actually have an effect. And it's sort of the beauty of excitatory and inhibitory neurons. The inhibition can cancel the excitation, and the fluctuations can now give you fluctuations in time and variability in firing. Okay, so the stuff I just gave you is pretty tough. It's far from trivial. You have to go through it yourself about 10 times before it all sinks in. But once it sinks in, it's one of the most important things you can know. Sums of random variables are incredibly common in all of science. So I strongly suggest you look at the notes. There's some hard pieces and easy pieces. Pick out the easy pieces and make sure you understand this. If you learn nothing else in this class, I'll be very happy. Okay, so we have about 5 minutes. And I'm going to give you a really quick preview of what we're going to do. We're going to now consider structured connectivity. So structured connectivity, oops. So structured connectivity okay, and in particular, we're going to consider something called the Hopfield network. And I'm going to consider this isn't initially going to look much like neurons, but eventually we're going to make it look like neurons. So SI is the basic activity of neuron I. Going to do discrete update equals sine of the sum on J of Jij Sj. Okay, this is our model. So SI of T equals plus or minus 1. We think of plus 1 as firing, minus 1 as silent. Although it's kind of not a good model because its firing would be at the maximum firing rate. And so if Jij were random, we get it's kind of uninteresting, right? If Jij is random, we just get some kind of, some random number there like we had before. It's a Gaussian random variable. It's really uninteresting. So what we're going to do is that Hopfield's sort of insight was there are certain Jijs that have really nice properties. So first of all, let me tell you what we're looking for. So if we think of I'm going to tell you this and then we'll end. So if you think of sort of, even though this is binary, think of this as S space. Okay. And one way dynamics can be interesting is if it's got lots of different fixed points. So if under this dynamics, you can float toward fixed points, in the Murray start, you might end up there. There might be another fixed. Might be another fixed point over here. Another fixed point over here. So if we could choose the weights to have these fixed points, this really looks like a memory network. And not only that, something called content addressable. Okay, which means if you start here, you'll end up here. If you start here, you'll end up here. And that's kind of nice because this is sort of the way human memory works. You know, you see a tail of a dog, you picture the whole dog. You see, you glimpse your friend from a distance, you can picture your whole friend. And we believe this is kind of what's going on in the brain. So seeing the tail of a dog starts you off with some initial conditions, and then network dynamics under this thing takes you to, aha, it's a dog. Okay. So what we're going to do next time is consider a particular JIJ that's going to actually give you lots and lots of fixed points. And that is currently the leading model for memory in the brain, although, as we'll see, there are problems. Okay, so let me stop there. Next time we'll do Hopfield networks. And again, we're going to use some of these tricks with sum. So if you didn't follow the sort of the last 20 minutes of the analysis, where I analyzed these sums, please look at the notes and make sure you understand that, because it's going to be critical for pretty much almost everything I do for the rest of these lectures. Okay, stop here.
Sorry, Prof, I have a problem.
Sure.
I wonder what the squiggle eye is.
Squiggle eye, so that's where squiggle eye. So squiggle eye, I should have written it down. It's basically, it is a zero mean unit variance independent random variable. Okay, it's just a random variable. For every I, it takes on a different value. It's a Gaussian random variable, but that's a little bit of a detail. Did that answer your question?
Maybe I'm not quite understanding.
So if you look at the equation for delta HI up here, so because of this Wij term, every single I is going to give you a different H. Every single I, delta HI is going to be different for every I, right? As you change I, you'll get a different value. And because these are completely random, the different values of delta HI is basically a random variable. And it's got some distribution. So if you actually did this and you made a histogram, so if you basically, so if you plot a delta HI or P of delta HI, what you'd see is it's basically, this is 0. It's got some range of values, right? So this is a histogram. With K elements. Okay. And what we're doing actually is computing the width of that histogram. Okay. And the width is what we calculated. And basically we can think of this as just a random variable. I mean, it's not really a random variable because it depends on dynamics, it depends on equilibria, but it effectively is. Okay. Every time you have a different I, you'll get a different number. It's pulled from this distribution, and that distribution is given by It's just basically, oops. So the sort of the standard deviation of that curve is given by this term, and squiggle I is just the random variable that sits under that curve. That kind of makes sense?
So it means that H is a little away from the reasonable distribution, right?
Wait, sorry, say that again.
Is the squiggle I means the real H is a little away from this theoretical distribution of it.
Yeah, I think so. I mean, basically H, of course, let's go up a second. H has this non-zero mean term here, right? On average, H is that value. So another way to think of it, so maybe this will be more helpful. So if we plot H, so this is now P of H. But P of H. So this term here is KW bar. Okay. And then around that, there's a distribution. Okay. And the width of this is what we computed. And the width of this is root K variance of W, nu squared bar with the 1/2. Okay. So we know it's got some distribution. We don't know what distribution, well, and we basically computed a standard deviation of that distribution, and the different values of in the squiggle I is just basically drawn from that distribution and then scaled by this number. Okay. So to find a particular value of delta H, sort of on average, we draw from the distribution a zero mean unit variance distribution and scale it by this quantity. Does that make more sense?
Okay, thank you, Frost.
Sure. Yeah, it's not, it takes a couple times of going through this yourself before it actually sinks in. I've been doing this for 30 years, so it finally sunk in, but it's not going to be easy.
Okay. Thank you, Professor.
Okay, thanks. As usual, I'll put the notes up.
Okay, bye.
The videos, but it'll be up soon. Okay, thank you.
Bye.
Bye.